Hi everyone, welcome back to E54. Today we're going to talk about lecture 14, which is electronic properties of materials. So in today's lecture, we're going to talk about how we characterize conductance and resistance of materials. We'll also describe what are the physical phenomena that distinguish between conductors, semiconductors, and insulators. These are a lot of the same materials we saw already, just a different way of categorizing them. So for metals, we'll talk about how conductivity is affected by imperfections and other defects, temperature, and deformation. For semiconductors, we'll discuss how conductivity is affected by impurities. These tend to be things like adding in dopants or other alloying elements, and temperature. So the place to start with is the basic equation for electrical conduction. This is known as Ohm's law, and it says that the voltage is equal to the current multiplied by the resistance. Okay, so the way you can think about this is that when I apply a voltage to a sample, how much current flows through it depends on the resistance of that device or piece that I'm talking about. Okay, so the units of voltage tend to be joules per coulomb. Current is sometimes called amps, but that's just coulomb per second. And resistance is given the name ohms. So you can tell that Ohm was a pretty important person in developing this law. So this is the way we typically learn about conduction in maybe a physics class or a baseline engineering class. But one issue is that this resistance contains both information about what material I'm using, but also the geometry of the sample through which that current is flowing. So more often when we're thinking about materials, we want to talk about something that's just a true material property. It's independent of sample size and geometry. Analogous to resistance, but a material property is what's called resistivity. Usually has the symbol rho. So resistivity has the equation. It's just the resistance times the surface area through which we have current flow divided by the path for that current flow. We will also see oftentimes the conductivity of your material described. The conductivity is just the inverse of the resistivity, okay? So just to get a better sense of that, let's sort of look at a simple example and say, I have two cylinders of material. They're made out of the same material, so they have the same resistivity. What's the resistance of these two pieces? So we can go in and calculate what that resistance is. It's going to be related to what's the resistivity, the length over which the conduction has to happen. It's 2L in this case. And then the area. So in this case, it's the cross-sectional area. So we get some value. Don't worry too much about what this is. What we really want to do is make a relative comparison. If we do that same calculation for this shorter, wider cylinder, what we'll get is a value which has those same terms, but that is a lot smaller. So this resistance of this second blue piece is 8 times smaller than the resistance of this green cylinder at the top. So you can think about this as analogous to flow of water in a pipe. If I was trying to push water through these two pipes, this smaller one might be too small. And it's going to take some time to press that water through it. Whereas this shorter and wider tube is going to be able to carry more water quickly, okay? We're not carrying water, and this isn't even a tube, but what we're doing is we're trying to carry electrons through this piece of material. So the same idea pops up. Another way to state Ohm's law is shown on this slide. We can express the current density, which is current divided by the surface area, so I over A, those equations we talked about, as being equal to the conductivity multiplied by something called the electric field potential. This isn't all that crazy. It's just how much does the voltage drop over the length of that piece through which it's going through. Okay? So just a different way of reformulating that equation. And if you go in and plug in all those intermediate equations, you can move back and forth between them. This current density is kind of, this is a flux, and it's kind of analogous to what we saw when we saw diffusion flux in an earlier lecture. So the current carriers that we'll talk about, and we'll see specific examples. So almost all solids have current being carried by electrons. In some cases, ions can also carry current as well. So just to orient ourselves, let's think about these different material classes that we've been talking about. We've been talking about metals and ceramics and polymers. So most metals have a really high conductivity. Okay, so the individual, for this discussion right now, the number in front here doesn't matter all that much. We're really mainly zooming in on or thinking about is this order of magnitude. So it's 10 to the 7th conductivity. So it's relatively easy to have electrons moving through. Ceramics are on the other end of the spectrum. So these could be things like glass, concrete, or aluminum oxide. These are in the range of 10 to the minus 10 conductivity. Okay, so that's not a small difference. The difference between these things is 17 orders of magnitude. Right, that's a huge, earth-shattering difference. Polymers tend to be relatively low as well. So it's really hard to get current to flow through a polymer. Now, something we hadn't seen before is a class of materials called semiconductors. We had just really lumped these in to ceramics when we were having these discussions. But when you start to think about electronic properties, these things fall out and have their own life. So things like silicon, germanium, and gallium arsenide fall somewhere in between the extremes of metals and ceramics in terms of conductivity. So it might be 10 to the power 0, 10 to the power of something small negative, -4, -6, but it's in between a conductor and an insulator. Okay? And oftentimes, we won't even talk about metals and ceramics by themselves. We'll talk about them as either conductors or insulators. This little plot is just showing a slightly different way of characterizing our materials. We've broken things down into which things are ductile, which things are brittle, all kinds of different categorization schemes. Talked about chemistry and polymers. You can also do that with electronic properties. You can break down materials and categorize them based on those properties and arrange things into different bins. So a major thing to think about and understand why we have these differences in conductivity is we need to understand the different mechanisms. So generally what we want is electric charge to move from one end of our sample to the other, okay? And there's a lot of different ways that this can happen. So these electrons can directly move. A good example of that, and maybe the easiest way that this can happen, is electronic conductivity in metals. So we mentioned that we have this electron C, so this area around all of the nuclei where the electrons are freely shared. So it's pretty easy for these things to just move around and migrate. The next step up in difficulty would be electronic conductivity in semiconductors. So again, we still have these electrons in this valence band around out here. These things can move in between the gaps of the different ions and find their way through the material. Another mechanism is that you can have ionic conductivity. We mentioned in a lot of ceramics, for example, we had positive and negatively charged ions. If these two ions switch places, we're going to have a net charge move within our material. Now, if you look at these pictures, what you can see is that generally, as we go down this list, each of these mechanisms is going to be a little bit slower. So in one case, the electrons are already free, they can move around. In another case, they need to break away and find some path through the material. In the next case, you need to actually have long-range diffusion inside of your material. So these are all possible. They can all carry current, but as we move downward, we're getting slower and slower and more difficult. What I'm showing on this slide is just wanted to point out that you can find a lot of different variables and units as we talk about electronic parameters or electronic properties. We'll mainly be talking about things like potential, current, resistivity, and conductivity. But if you see something like the permittivity, don't worry too much. These are just a different set of descriptions of the electronic properties of your material. Okay, just as an example of where this can be useful in a real engineering sense, if you had a wire of copper, you could add, and you knew sort of how long it was. In this case, it's 100 meters, right? That's a long distance. This would be something like, trying to connect two houses or something like that. And you know that you want to be able to have a certain amount of current go through that. You could say, what's the minimum diameter of the wire so that over this long distance, I only have a drop in voltage of less than 1.5 volts. We could just use those different expressions of Ohm's law that we came up with. I'm just showing how we can sort of arrange it and isolate what we were given in this problem. We were given the current. We were given the target change in voltage. We were told the material, which means we can go and look up what the conductivity is. And we were given the length. So the only thing we don't know is this cross-sectional area. Really, what we want to know is the diameter of that wire. So this is a simple way, if you were asked this problem, go and you solve for diameter in this problem, and you'd find that your diameter has to be larger than 1.87 millimeters. Right? All right. So as we build up our understanding, I just want to remind us all of something we talked about in one of their very early lectures. I believe it was lecture 2. This is the fundamental concept of electron orbitals. So we discussed this idea that electrons have wave-like and particle-like properties. That means that they have these orbitals with a defined probability of where they are. We can describe these orbitals by their energy levels and the quantum numbers that describe those. And again, as we mentioned, if we go up in quantum number, for example, we get to higher and higher energy orbitals, right? And we also mentioned this idea if first we fill the electrons closer to the nucleus, those are very tightly bound, and then we start to fill the outer valence bands of our material. And then we also talked about how, for example, if you go to these higher bands, you can start to fill in. If you can go from just n equals 3, you'll have one base energy level. And as I add more and more electrons, I can fill slightly different energy levels around that n equals 3 baseline. Right? So this ends up being really important for electronic properties, because this way of filling these orbitals and these energy levels ends up giving us what are called electronic band structures. So on this far left is just the description of what would happen with one atom, okay? These are the energy levels which are filled by electrons. So there's the core energy levels, and then there's some energy level that's filled in a valence band, okay? If I take and I put two atoms really close to each other, the core levels look very much the same, but those valence bands, they can't have exactly the same energy. So they're going to have a slightly different quantum number, and they're going to have energy levels which are similar but slightly separated, okay? If instead of 2 atoms, I add in 6 atoms, this same process happens. You start to see that we're developing a collection of possible energy states high and a collection slightly lower, right? In a real solid, we often have many millions of atoms, so we're not going to see those discrete lines. Instead, what we're going to see is these bands. These are possible energy levels that can be filled by electrons in that valence band. Okay. So the way to think about this, a different way of visualizing this, is if you think about having just 12 atoms and think about what their energy structures look like as a function of interatomic spacing. Let's start far out here on the right side of this. So this is where we have these 12 atoms, but they're very far apart from each other. In this case, they're not interacting with each other, and you just have these discrete energy bands, which look like those baseline orbitals that we talked about. The 1s electron state, the 2s, and everything does its own by itself, often a vacuum. As these materials get closer and closer to each other, you start to see splitting of these possible bands that can be filled, right? And this is just telling us that we have some interaction once the atoms get close enough. This is another view of this for how these bands might look. Again, with instead of 12 atoms, maybe millions of atoms. We'll start to get these different energy levels. And if we pick a given location along the x-axis, this could be the equilibrium interatomic spacing for our crystal structure, we'll see that as we go up, we'll Low levels just hit one single energy level. Higher levels will hit this band right here. This is what's called the valence band. So this is what's filled. In this case, there's a gap in the middle, and then we will hit this top yellow band, which is the conduction band, okay? Now, this region right here is what's called a band gap. So it's just some space in between this valence and this conduction band, which isn't a possible option for electrons to fill. Now you can imagine, even for the same types of atoms, if I change this interatomic structure and come out here, I don't see those bands. And if I come way down here, I can find a place where there isn't a band gap. So where the blue and the yellow overlap. So these different possibilities of having different types of band structures is exactly what gives us this separation of material behavior into conductor, insulator, or semiconductor. Okay? Conductors are pretty simple. There's just empty energy states, which are right next to the filled states. There's two ways this can happen. You can have a band gap inside your possible energy structures, but it's high and away from where the fun action is happening. Usually where the action is happening is at something called the Fermi level. So this is the highest filled energy level. And in this case on the left in part A, the filled states, so this, for example, one orbital set is only partially filled. So there's some filled states going up to here, and then there's some empty states right above it. Another possibility is you could have a situation where you don't have a band gap at all anywhere near your Fermi level. And in fact, your filled band and the next empty band overlap with each other. That's fine too. In both cases, these blue regions represent empty states which can easily be filled with electrons. An insulator is a little bit different. It has a fully filled valence band, a gap, and then this empty conduction band. So this is where electrons would need to be to move around. Semiconductors qualitatively look the same. We have a filled valence band, a band gap, and then an empty conduction band. The only difference between an insulator and a semiconductor is how big is that band gap. In a semiconductor, it's relatively small and we can jump over it and have conduction. In an insulator, it's relatively big and we can't get over that barrier. So let's start thinking about how these things happen. We'll start with conductors. So these are, again, generally metals. So we can, again, have a partially filled valence band. When electrons are moving locally, they need to move into a higher energy state, but there's lots of options here, either in that partially filled band or in this empty band that overlaps. So the way this happens is thermal fluctuations can give this little electron just enough energy to pop into this higher energy state. This is a view on the energy sort of graph. And spatially, this would mean that this electron is migrating through this chunk of material. In an insulator, you can have some temperature giving you some fluctuations. This electron might want to try to jump out, but it can't overcome that gap. A rough order of magnitude or a rule of thumb is that an insulator is a material with a band gap that's greater than 2 electron volts. Semiconductor, if you have a band gap that's smaller, these thermal fluctuations may be able to pop this electron out over that gap and into that empty band. So we can start to see how some of the different microstructural features affect conduction in these different materials. And let's start with metals. Impurities and vacancies. These all, in metals, tend to increase our resistivity. So they make it harder to move electrons around. You can see this in this plot on the bottom. On the y-axis is resistivity, on the x-axis is temperature. Let's just take a given temperature for now. We'll think about changing temperature yet. So pure copper has a relatively low resistivity. If you want to think about it in terms of conductivity, it's a high conductivity. It's easy to conduct current. That resistivity increases as we jump to this green, blue, and red curves, in which case we're adding more and more nickel atoms. Now we can remember that copper nickel is a good substitutional solid solution system. So we're not creating phases or new interfaces. We're just adding in substitutional atoms. But we're getting these huge changes in our resistivity. You can also get a change by deforming your material. So if we look at this solid green curve, this is for copper with 1.12 atomic percent nickel. If we take and deform that same sample, the resistivity goes up too. So remember, when we do deformation or cold working, we're increasing the number of dislocations that's in our sample. So we're adding obstacles to those electrons. Now, temperature also tends to increase resistivity. If we look at any one of these curves, as the temperature goes up, the resistivity goes up. We'll talk about the mechanism, but I just want to point out very clearly that metals and semiconductors have a different dependence on temperature. So the way we can understand this is think about what's actually happening. So before we were talking about energy levels and jumping into those open states, but again, spatially, what we're talking about is this electron moving from one end of my sample to the other, okay? Now, as it does this, unless it's perfectly aligned so that it can pass through that open space, if we just have an arbitrary path, it's gonna, every once in a while, hit an atom and have one of these collisions. In this case, it has 3 collisions, okay? Now, the more collisions we have, or these scattering events, the harder it is for that electron to make its way from the left to the right side of the sample. In a way, you can think about it as shown on this plot here with electron velocity versus time. So the electron's trying to fly through until it hits something, then it has to slow down. And every time it hits something, it has to slow down, okay? Now, if we add increased temperature, so we raise temperature of our system, what happens is we're adding thermal vibrations. So rather than those atoms being locked into one location, they're vibrating in all different directions. Now, generally what that's going to do is mean that as this electron moves its way through, it's going to hit more and more atoms. So instead of 3 collisions, it has 6. And the same type of thing happens when we're talking about adding something like a vacancy, or in this case, it's an interstitial impurity. We swell the lattice, and it makes it more likely that we have more collisions. In this case, 8 collisions occur. The key thing here is that moving the electron itself is not all that hard. It's just about the path that that electron takes. This is true of metals. This is just showing another way of visualizing this. So if that electron can find a smooth way through the system, the conductivity is very high, the resistivity is low. If you have lattice strains or other elements added in there, it can make that path more tortuous. Now, one interesting correlation with this is that, remember, we add defects to make our material stronger. So generally, the things we do to increase the strength of our material tend to decrease the conductivity. So you can, just to see how these things interact with each other, for example, you could be asked to go and estimate what the electrical conductivity would be for a copper nickel alloy with a given yield strength. In which case you could go and read off that yield strength, figure out that this is representative of a copper nickel with 21 weight percent nickel. Find a similar type of curve of either resistivity or conductivity, and for that 21% nickel, read off what your resistivity is. If it's resistivity, we have to remember to take the inverse to find the conductivity. But we can think about how these are related. So semiconductors are a little bit different. So generally, if we look at data for semiconductors and we plot conductivity as a function of temperature, what we'll see is that increasing the temperature increases the conductivity. And this is, just a reminder, this is opposite to metals. The reason it's a totally different behavior is we're not talking about electrons that are easy to move, and we're just making the path a little bit more difficult. We're actually talking about a situation where it's difficult to even get those electrons moving. So we have to remember that in semiconductors, there's a band gap. We have to jump over that gap to get into this conduction band. So that conductivity is really related to that energy barrier. And in fact, the conductivity of semiconductors is generally proportional to the exponential of negative the energy gap divided by KT. So this is that Arrhenius equation we've seen over and over and over. If we have some energy barrier we have to jump over, increased temperature gives us a little thermal boost to pop over that gap. So intrinsic semiconductors are materials that have this behavior by themselves. Silicon and germanium are good examples of single element systems that have this type of behavior. You can also find lots of compounds. So gallium arsenide, indium selenide, cadmium and sulfur, and zinc and telluride are other good examples of compounds. Now, generally, the wider the electronegativity difference between the elements, the wider the energy gap. In semiconductors, we should also think about what happens once that electron jumps into that conduction band. So we mentioned in this valence band, this electron, if it has enough thermal energy, it can pop up into that conduction band and become a free electron. Now, when it does that, it creates what's called a hole in the valence band. So this is a place where there originally was an electron, and now there's a lack of an electron, okay? Now, generally, these things can both migrate. And generally, we also said that higher temperature promotes more electrons jumping into that conduction band. So that last slide was showing you the energy levels we're jumping between. Again, let's think about what's physically happening inside of our material. What's shown on this slide is silicon. So the pink spheres are just the silicon atoms, and the black spheres are the valence electrons around them. When there's no applied electric field, everything is sort of static and stagnant. If we apply an electric field, you can start to have electrons and holes migrating. So in this case, where there used to be an electron right here, it's jumped out and starting to move to the right. And when it does that, it creates a hole at the site where it used to be. Now, as we go forward in time, that electron keeps migrating to the right, that hole keeps migrating to the left, and eventually we're carrying charge to the sample. So this electrical conductivity in a semiconductor is really from a combination of effects. The conductivity is related to how many electrons we have, so what's the density of electrons, their charge, and the mobility of those electrons, but also how many holes we have in our sample, multiplied by that charge, multiplied by the hole mobility. Now, in each case, the charge is the same. It's the magnitude of the charge of one electron. But we can talk about the density and the mobility of either the electrons or the holes in our sample. And again, these are connected to how easy it is to move around charge through our system. So we would rather have a direct path than a confusing, tortuous one. So electrons generally have a higher mobility than these holes. This probably makes sense because it's a more direct path. But these types of mobilities also interact with impurities in the same way that an electron just flying through a metal did. So if we think about what happens when we add more and more impurities, our mobility of our electrons and our holes goes down. Because again, it makes that you have more scattering events, and that makes that path more complicated. Similarly, if you increase temperature, it generally reduces the mobility of those electrons and those holes. So this is just showing different sets of data for different impurity concentrations, but the vast majority of this data generally goes down as we're going to the right and increasing the temperature. So the mobility of the electrons and how difficult it is to move them around consistently goes down as temperature goes up. So in intrinsic semiconductors, the number of electrons and number of holes has to match. And a way of writing that is that N has to be equal to that P in that equation I showed you for conductivity 2 slides ago. So this is the case for pure silicon. These things have to balance. Extrinsic semiconductors are materials where N is not equal to P. So the number of electrons is not equal to the number of holes. And this can occur when you add in impurities with a different number of valence electrons than the host. If we stay with this example of silicon as our base material, we can think about that situation we talked about with our nuclei and our valence electrons hanging out around there. If we go and replace one of those silicon atoms with a phosphorus atom, so phosphorus is 5+, we're effectively adding an extra electron into the system. Okay, so now there's an extra electron that can move around without creating a hole. In contrast, if I replace a silicon atom with a boron atom, so boron is 3+, even in the state where there's no electronic field applied, there's an extra hole in that system. Now remember, when we are doping some material, we're not adding one phosphorus atom or one boron atom, we're adding 1%. So that means that there's still maybe thousands or tens of thousands of these atoms, these extra electrons or extra holes in our sample. So for a material where we've added phosphorus, we're going to have way more electrons than holes. So our conductivity is going to be dominated by the behavior of those extra electrons. In comparison, the p-type semiconductor, where we've added a bunch of boron, has many, many extra electron holes. So the conductivity is controlled by the behavior of those holes. So again, these are just called N and P type because we have extra electrons and extra holes. The N and the P just comes from that equation where those describe the density of either of these features. So we can think about how much easier this process is by showing this schematic. This is showing different times progressively as we change the electrical field. So in this case, the phosphorus atom that's been added has an extra free electron there. And this guy can just move around and move to the right and shift around without creating any holes inside the sample. So if we think about what this means on this energy perspective, we have this filled valence band, this band gap, but we have this extra electron in there. So it's an extra donor state, which is up near that conduction band, and it's relatively easy for it to jump into that. So it doesn't have to jump across this whole band gap, it just has to jump across this little region right here. It's very easy for it to be added. For the boron, the boron dope sample, we have this extra hole, and this can move around inside of our sample. In terms of energy, this means that we have an extra acceptor state. So we have all the states that are filled, and then it's very easy for some electron in that valence band to jump up into that new acceptor state. So what we're effectively doing is changing the energy gap that we have to jump over. We don't have to jump over the whole band gap for these N and P type doped semiconductors. We just have to jump to either an acceptor state or jump from a donor state to the conduction band. So with this, we can start to see what the data looks like for doped semiconductors. So here again is showing conductivity versus temperature. The blue line is the data for pure silicon that we saw before. Temperature increases conductivity. We can start to see that it's a little bit more complicated when we're talking about doped semiconductors. So first of all, as we add those boron dopants, so we go from pure to a very small amount to a larger amount, the conductivity is popping up quite a bit. So adding more of those impurities is a good thing. And generally, it complicates that effect of temperature. So we see that down at these low temperatures, the conductivity is much higher, and it doesn't follow this same type of behavior as the pure silicon. But as we increase the temperature, eventually we just follow that pure silicon type of response. Okay. So the way of thinking about this is that we really have a few different mechanisms coming on. So if we make a different plot, we can plot what the conduction electron concentration is as a function of temperature, and plot what happens for doped and undoped silicon. So at very low temperatures, for undoped silicon, pure silicon, the conduction electron concentration is 0. There's not enough energy to get over that band gap and have electricity go through. Now, at some point, it starts to increase, and this can be what's called intrinsic behavior. So it's just telling us how, as the temperature goes up, it makes it easier for those electrons to jump over. Great. In high temperatures, the doped follows that, but at low temperatures, it has a non-zero conduction electron concentration. So at these lower temperatures, those extra donor states or acceptor states can move around freely and conduct electricity in our sample. Now, if you cool down enough, you can shut off even those mechanisms. So this very, very low temperature regime is what's called freeze out. So that's where thermal energy fluctuations aren't even enough to excite electrons into those donor or acceptor states. So that intrinsic carrier concentration is what's increasing as we increase the temperature, and it goes up orders of magnitude in this range. And again, this type of behavior is what leads to this intrinsic regime of electron concentration with temperature. Okay. So this is all very useful, and one cool way that engineers can use this is to make what's called a p-n junction. So the idea here is that we want to create a material that has p-type material on the left side and n-type on the right side. So on the right side, there's a bunch of extra electrons. On the left side, there's a bunch of extra holes. And the rationale for doing this is we can make a little interesting circuit, or what's called a rectifying junction. So if we apply current in a certain direction, what we call the forward bias, we will push these extra holes near that interface between the two materials, and at the same time push those extra electrons near that interface. Now, to get electricity to conduct through this sample, when it's in the blue, it can move by these extra electrons. But these extra electrons can only go a short distance past that interface before they run into trouble. Because over here, remember, is not the right type of material. So they don't want to move way over into the sample. But by having these populations of holes and electrons near each other, it makes it very easy to get current to flow all the way through this. We can contrast that with what would happen when we apply what's called a reverse bias. So we switch the voltage that we're applying to the sample. In this case, the holes are being pushed to the left, the electrons being pushed to the right. So there's a low concentration of those extra features at this interface. And basically what happens is in one area, the holes can migrate around, but there's not enough to get them to migrate and transfer that charge off into the other side of the sample. The effect is in that when we have a forward current or a forward bias, we have relatively easy flowing of the current. When we have a reverse bias, we have very little current flow. Now, one thing I want to point out is these are drawn as sort of putting a p-type material up against an n-type material, but practically we often don't just take two materials and slap them together. What we usually do is take one material and dope it differently on these different sides. So this is one block of material where we've diffused boron into one side and phosphorus into the other side. The rationale for that is that interfaces themselves, and that's what you would get if you glued two materials together, can actually change your electronic properties as well. So the sort of performance you would get from this is shown here on this plot to the left. So current is on the y-axis, voltage is on the x. So as we apply the forward bias, we're applying more and more voltage here, the current goes up. Okay. Now, if we take that same amount, in this case called voltage naught, and apply it in the reverse direction, we'll see very little current. Okay. There's some small amount of current that flows, but it's not much. Now, this effect will eventually break down. If I apply enough voltage, I can break down this effect and then get voltage and current to increase along with each other. The reason this is one example of a reason this is really useful is that this can take an alternating type of what would normally be alternating voltage and current and turn it into a direct current. So if you apply some voltage waveform that goes positive, negative, and so on and so forth, you're going to get current in that direction flowing well in one direction and then very little in the reverse. Very well in one direction, very little in the reverse, and so on and so forth. Now, this is something that's used very often to make integrated circuit devices. So these are often made in a very complex manner on a chip. So this is showing a cross-sectional view of an integrated circuit. These black regions are going to be metals, so these are conductors. On the bottom, there's maybe it's been diffused with the right type of alloying element to make it p-type silicon, and then your substrate is n-type of substrate. Now, these are often very small. In modern integrated circuits, these little features are often tens of nanometers across, and you can have hundreds of millions of components on a chip. And then the other thing is that these can be stacked layer by layer. So if these are very thin films, you can have different layers of chips on top of each other. So just as a summary of what we talked about today, so electrical conductivity and resistivity are material parameters and they're independent. So we don't want to talk just about resistance by itself because this incorporates geometry. And conductivity and resistivity are the inverse of one another. If you want to think about it, conductivity is how easy it is to move current through a sample. Resistivity is how hard is it to move current through a sample. When we try to classify materials in terms of these properties, we usually do it in terms of conductors, semiconductors, and insulators. And these really differ by what are the accessibility of energy states for those conductance electrons. For metals, conductivity is increased by reducing deformation, reducing imperfections, and decreasing temperature. For pure semiconductors, conductivity is increased by increasing temperature or even doping. So doping is not always a bad thing. If we add the right type that can make our material P or N type semiconductor, that can increase our conductivity. All right, with that, we're at the end of today's lecture. Look forward to seeing you in a Q&A session soon and answering any questions you have. Have a good day.